Hello, my dear students. So, in the last chemistry class, we have started with the new chapter called as solution. I think all of you have seen the video and you have understood the concept, right? So, we will go with the continuation of the concept. So, I'll revise what we have studied in the last class. I have started with the definition of solutions, and also we have seen the components of solution, that is solute and solvent, and also we have seen the different types of solution. So based upon the different types of solution, how many possible solutions are possible? So totally 9 types of solutions are possible, right? So also we have seen concentrations of solutions. What do you mean by concentration of solutions? It is the amount of the solute present in the known quantity of solvent. We also have expressed different types of concentration of solutions. That is, we have started with the mass percentage, that is W by W, and second one is volume percentage. Then third one is mass by volume percentage. We have saw some of the examples of these concentrations also, and I also have discussed regarding the concentration of solution of molarity by using molarity represented by capital M, and also molarity represented by small m. So if you have not understood the previous concept, please go through the video, or you can ask me or reply me, right? So we'll continue in this class with respect to the concept, that is molarity. In molarity, as I had explained already the definition. There is one more thing which you should know regarding the molarity. That is, molarity is temperature dependent, right? So here, what does it mean by temperature dependent? That means if molarity of a solution is increasing, the temperature also increases, or if increasing temperature, the molarity of a solution also increases, right? So m is directly proportional to T, right? And similarly, molality is independent of temperature. That means if temperature is increasing, molality does not increase. So please do remember, children, in one of the board examination, they had asked regarding 1 marks question for how molarity of a solution is dependent, right? So it is whether it is dependent, right? So you can write the answer is dependent, because so increasing temperature increases the molarity of solution. Now the next we go for the concept called as what, that is one of the concentration of solution, that is called as parts per million, which is represented by the symbol ppm. So in how to define this parts per million, right? So we'll go for explanation for parts per million. What is the definition? So here you can see parts per million is defined as the ratio of mass of solute to the mass of solution into 10 raised to 6, or represent, we can simply say the number of parts by mass of solute present in 1 million, that is 10 to the power 6 parts by mass of solution, right? So I think you have understood the definition. We can define it as what, the parts per million is the ratio of mass of solute to mass of solution into 10 raised to 6, or number of parts of solute present in 1 million parts of mass of solution. So here is a simple example, right, regarding the ppm. So here it is, the problem is 600 gram of water contains 4 gram of magnesium ions. Express the following in parts per million. So we know the formula. So mass of solute here given is 4 grams. Mass of solution given is 600 grams. So into 10 raised to 6. So when you simplify this, you'll get the answer as 6.622 into 10 raised to 3. I have converted the decimals, right? So into 6.622 into 10 raised to. Now similarly, we'll go for one more example, right? So regarding the parts per million, that is if 250 grams of water contains 7.5 grams of aluminum ion, express the following in parts per million. So the same formula we apply, that is the, it is the ratio of mass of solute. Mass of solute here is 7.5 grams, and mass of solution is 250 grams into 10 raised to 6. So when you apply, you will get the result as what, 0.03 into 10 raised to 6, or you can convert into, you are shifting the two decimals, so that will also be equal to 3 into 10 raised to 4. right? So these are simple problems related to that of your parts per million. Now, apart from that, you should also know that there is one more uh, thing regarding the parts per million, right? So that is this parts per million or ppm is independent of temperature, right? So remember student, ppm is said to be as what? Independent of temperature, and it is widely used in the application of environment, or it is an environmental application, right? So I think we are clear with the concept of parts per million. So we go for the next and the last type of concentration of solution, that is called as mole fraction. Now we go for definition of mole fraction. Before that, what is the symbol, right? Most of you may think that is this is x. No, it is not an x. It is a Greek letter which is called as what? Chi, right? So mole fraction is represented by the symbol chi. Now coming for what is the definition of this mole fraction, right? So here we can see here. So we'll go for the definition. So definition states that it is the ratio of number of moles of solute to the total number of moles of solution. So I repeat once again, it is the ratio of number of moles of solute to the total number of moles of solution. Now please do remember children, right? So I'll be explaining here the concept clearly. So just understand this. So we know number of moles of solute. Now say for example, I represent the solute as N2. So here you can see if N2 is number of moles of solute and N1 is number of moles of solvent, then if chi 2 or mole fraction 2, right, is a mole fraction of solute, and mole fraction 1 is said to be mole fraction of solvent, then according to the definition, right? So mole fraction of 2, here 2 represents what? It is the number of moles of solute, or mole fraction of solute. So that is equal to number of moles of solute. What is the symbol for number of moles of solute? It is N2 divided by number of moles of solution. Please do remember children, here it is solution, not the solvent. So for solution you have to take what? N2 plus N1. So why N2 plus N1? N2 is the number of moles of solute and N1 is the number of moles of solvent. So together they make as what? Number of moles of solution. So this is for what? Mole fraction of solute. Now similarly for mole fraction of solvent, so it is a ratio of number of moles of solvent to the number of total number of moles of solution. So number of moles of solution is N2 plus N1. So here N1 is representing what? Number of moles of solvent. So here we have two formulas for solute and solvent. So mole fraction of solute is given as number of moles of solute to total number of moles of solution. Mole fraction of solvent is given as number of moles of solvent to total number of moles of solution. Now this is the important one. We'll also need to solve some of the examples for this, right? So we'll go for some of the examples for the mole fraction, right? So here, first one you can see here, the first problem is, what are the mole fractions of glucose and water in a solution containing 5.65 gram of glucose dissolved in 25 gram of water, right? Please clear, please students read clearly the question. You have to calculate the mole fraction of glucose as well as water, in which the glucose is present 5.65 gram and water present is 25 gram. Now for how to solve the problems related to this, now you can see here, first we are going to calculate the number of moles of glucose. What is the number of moles of glucose formula? We know we are studying first year also. So moles is given by mass of solute, number of moles of solute by molar mass of solute. So here, so what is the quantity of solute present here? It is 5.65 grams. Now, molar mass of solute. So molar mass of solute here is glucose. So when I calculate the molar mass of glucose, that is nearly equal to 180. How did you get now 180? Right? So I just write it. The formula of glucose is what? C6H12 and O6, right? So here you can see you have to multiply for molecular mass calculation. So multiply 6 into molar mass of carbon is, it is a 12, 6 into 12, plus hydrogen is 1 into 12, and oxygen is 6 into 16, right? So when I simplify this one, you'll get the totally equal to what? 180, right? So you know how to calculate this one. So I substitute the value and I get the value as what? 0.03139. Now this is for what? Moles of glucose. Now, similarly, I will calculate the number of moles of water. So similarly, the same formula applied here, that is number of moles of solvent. So how much is the solvent? 25 grams. So I substituted. So molar mass of solvent is how much? 18. How did you get 18? So I have formula of water as H2O. So 2 into 1, and oxygen, that is 16. So 16 plus 2, that is equal to 18. So substitute this here. So you'll get the answer as 1.389. Now, I have not completed the calculation. I just calculated the number of moles of glucose and number of moles of water. Now, to get the mole fraction of glucose, we know what is the formula of glucose. Glucose here is what? Solute. So N2 divided by N2, N1 plus N2. So N2, 2 represent what here? It is a solute. So solute is glucose. N of glucose is equal to N of glucose plus N of water. Here N represents number of moles. So number of moles of glucose we have calculated, that is equal to 0.03139. So substitute here. So similarly substitute the values of N for water and glucose here and simplify. You will get the answer as what? 0.0221. Now this is what, dear students, this is the number of mole fraction of glucose. So we have calculated the mole fraction of glucose. Now similarly we need to calculate mole fraction of water also. Unlike here, same formula, but here it is a solvent. So number of moles of solvent. So solvent is water divided by number of moles of solution, that is solute plus solvent. So substitute here value 1.389. Why? Because we have got the moles of water value as what? 1.389. So substitute these values, you get as the mole fraction of water is equal to 0.978. Now this is very important, dear students. Is there any shortcut, right, to calculate the mole fraction, right? So there is a formula, that is, say for example, the mole fraction of solute plus mole fraction of solvent, that is always equal to 1. Mole fraction of solute plus solvent is always equal to 1. Now say for example, if I calculate the mole fraction of a solute, can I get easily the mole fraction of solvent? That is, how do you get? That is, I'm going to solve here some examples, right? So here you can see, I think I had solved this one. So here you can see, okay. So mole fraction of water is how much? Now if you want to calculate mole fraction of water, I've already calculated the mole fraction of glucose. So that is equal to how much? 1 minus mole fraction of glucose. That is 1 minus mole fraction of glucose is this value. So you get the same answer. So it's 0.978. So here also you can see that we have got the same answer. So it is easy to calculate if you calculate any one of the mole fraction, right? So hence the shortcut method to calculate one of the mole fraction is, if you calculate the one of the mole fraction of solute or solvent, you have to subtract with 1, you get the other one as a mole fraction value. Now we'll go for the second one. One more example will go, right? I'm solving this. This is very important one, mole fraction, right? So the second problem states that 9 gram of glucose is dissolved in 90 gram of water. Calculate the mole fraction of glucose and water in the solution. Everything is same here. What is the thing? It is given as the moles of glucose is how much? 9 grams, and that of water quantity is 90 grams. So unlike the same formula we are going to apply, first we are going to calculate the moles of glucose. That is, I substituted here 9 divided by 180. Why 180? Molecular mass of glucose is 180. So here the mass of solute is 9. So when I simplify, I get it as 0.05. Similarly, calculate the moles of water, that is number of moles of solvent. So that is, here they are given as a 90 grams. So 90 divided by 18. 18 how? I already told. So when I simplify, you'll get the answer as 5. So since we have calculated the moles of glucose and moles of water, now we can calculate the mole fraction of glucose, that is N2 divided by N2 plus N1, that is number of moles of solute divided by so number of moles of solution. When I simplify, substitute and simplify, I'll get the answer as what? 0.0099. Now, as I told earlier, mole fraction of water can also be calculated by using the formula 1 minus mole fraction of glucose. So if I substitute that, I think I solve this one. So here again I solved. So mole fraction of water is equal to 1 minus mole fraction of glucose, that is 1 minus 0.0099. So answer will be 0.99. So here you can see the same answer I got, 0.99. Right. So either you can solve like this, but to save this time, you can use the this formula. That is mole fraction of any one substance is equal to 1 minus the mole fraction of other substance. Right. We'll go for the last problem related to that of mole fraction. Now, what is the problem? Calculate the mole fraction of C6H6, that is benzene, in a solution containing 30% mass of CCl4, that is carbon tetrachloride. Now this is a little bit changed in the problem, right? So they have given not the quantity of solute and solvent, they have given what? The percentage of CCl4 in benzene. Now how to solve this one? Now we know that percentage is always in 100. Say for example, 100 gram of solution contains 30% of CCl4. That means what? Equal to 30 grams of carbon tetrachloride. If in 100 grams 30 gram is carbon tetrachloride, then remaining 70 grams should be equal to what? The benzene. It will be equal to what? Benzene. So hence in 100 gram we have 30 grams of carbon tetrachloride and 70 grams of benzene. So there is not much to confuse here. If they give percentage, directly they have given the mass of CCl4, that is 30 grams, the remaining will be 70. Now to calculate the same method here, it is a number of moles of benzene, right? So substitute here 78. How? Must multiply here 6 into 12, 6 into 1 we will get 78. So 70 is we know that it is present in the solution. So we get the number of moles of benzene as 0.897. Similarly, number of moles of carbon tetrachloride is equal to 30 divided by 154. You simplify this, molecular mass will get as 154. So that is equal to 0.195. Now to calculate mole fraction of benzene, the same formula. So benzene here is what? It is a solvent. So that is number of moles of benzene divided by number of moles of benzene plus carbon tetrachloride number of moles. So you simplify. I think we can simplify these two, right? So I'll not write the answer. You can easily simplify. Similarly, substitute here for carbon tetrachloride the same formula. Now if you calculate this, by using the same above formula, you can calculate the number of moles of carbon tetrachloride, or you can directly simplify this, right? So hence this is the problem related to that of your mole fraction. So I think you have understood the concept related to that of your mole fraction. So this was the last method of concentration of solution. So by using these methods, we can understand what is the amount of solute present in known quantity of solvent. Right? These are all important, right? So for 1 marks in your examination, many of times there are many questions related to these concentrations for 1 marks. So hence be prepared. Right? Okay. Then we go for the next concept, that is solubility, right? So before I go for solubility, right? So we'll see, right? So what is the next concept? Okay, I'll go for the concept of solubility. So I think you know, or it is a easy term called as solubility. What do you mean by solubility? So I define solubility as the maximum amount of solute that can be dissolved in a specified amount of solvent, and at that temperature is called solubility. Understand students, it is very easy, not much difficult. What is solubility? I'll explain in a simple way. Say for example, in 100 ml of water, if I want to prepare a sugar solution, the maximum amount of solute that can be dissolved in 100 ml of water is say 10 grams, right? So at that temperature, if 100 ml of water contains 10 gram of sugar, that is its solubility. So hence the definition only says maximum amount of solute. So in 100 ml, how much is present? 10 grams of solute is present. So that will be the maximum. So that can be dissolved in a specified amount of solvent. Here, how much is the quantity of solvent? 100 ml of water. So at that temperature, see, I'm not providing an extra temperature or reducing temperature at that temperature. So if maximum amount of solute is present in maximum amount of solvent, then that we say it as what? Solubility. I think you understood the example very easily, right? So now, solubility depends on the three factors, that is nature of solute, right? Nature of solvent and temperature. So temperature is very important here. I'll give an example related to that of a temperature when you go for the different types of solution we're going to study, right? So here, the factors which depends the solubility is solute, nature, solvent, nature, temperature. Increase or decrease may change the solubility of the solution, right? So next, based upon the solubility, we go for the next term called as a saturated solution. Now, what do you mean by saturated solution? It is a solution in which no more solute can be dissolved. Now, it is very simple definition. Saturation or saturated solution. It means what? It is a solution in which I cannot add still more amount or quantity of the solute, right? So as I had told in the earlier example, that is in 100 ml of water, the maximum amount of sugar can be dissolved is 10 gram. If I am going to add one more gram, that is 11 gram of sugar, the extra 1 gram of sugar will not be dissolved. It will be appearing in the upside only, so that you can observe clearly. So the 10 gram which is dissolved, right, in 100 ml of water, that is said to be as what? A saturated solution. So we say that as it has reached its saturation, right? So saturated solution is what? A solution in which no more quantity of solute can be dissolved. So that solution is said as what? Saturated solution. Now, coming for the next, unsaturated solution, opposite of that, it is sorry, here me should not come. It is the solution in which some more solute can be dissolved at the same temperature, right? So here there is a slight mistake. It is the solution in which it is the solution in which still some more quantity of solute can be dissolved. Say for example, in, as I told one example, that is in 100 ml, the maximum solute can be dissolved sugar can be added is 10 grams. So if say for example I added 8 grams of sugar, that means it has still capacity to dissolve the sugar of 2 grams. So that type of solution is said to be as what? Unsaturated solution. If a solution contains maximum amount of solute, then we say it as saturated solution. If the solution contains less amount of solute, then we say to be as unsaturated solution. Now there is a key point, that is a saturated solution can be converted to unsaturated by increasing temperature. And I think you might have observed this in your day-to-day life. That is, say for example, I have added 10 gram of sugar already in 100 ml of water. I am going to add one more gram of water, which is not going to dissolve. But when I heat that solution or increase the temperature of that solution, you can observe that that one extra gram of sugar will get dissolved. But when you are going to decrease the temperature, then again that extra 1 gram of sugar will be appearing, right? So a saturated solution can be converted into unsaturated solution by increase the factor of temperature. Now this is not permanent, right? It is temporary. Now we go for the next concept called as a solubility of gases in liquid. We know what is meant by solubility. What do you mean by solubility? It is the maximum amount of solute present in the maximum amount of solution. Now, what is solubility of gas in liquid? That means we are going to mix the gas in liquids. Now, I think I discussed different types of solutions. Under that, the example for gas in liquid, right? So the example which you can give easily is carbon dioxide gas in water. I think soda water you might be hearing, right? So or Coca-Cola or Pepsi, right? So when you open the top, the gas escapes. That means gas is usually present in that liquid. So hence it is an example for your gas in liquid. Now for solubility of gas in liquid, there is one important law, right? So stated by the scientist called as a Henry, right? So that we are going to study, right? So what is the statement? So we'll see that one. So for Henry's law, it states that at constant temperature, the mole fraction of gas in liquid solution. Now see here, mole fraction is represented by the symbol chi. So I repeat, at constant temperature, mole fraction of gas in liquid solution is directly proportional to partial pressures of gases, right? So I repeat once again the statement. It is very important from your exam point of view. One of the important law which will be asked, right? So remember the statement. So Henry's law states what? It is stating as at constant temperature, mole fraction of gas in liquid solution is directly proportional to partial pressure of gases. Say for example, the mole fraction of gas in liquid solution is given by Chi. It is said to be as what? Directly proportional to the partial pressure of gases. Now, what is the difference between a pressure of a gas and partial of a gas? I can simply say, right? If mixture of gases exhibits the pressure, commonly we say it as pressure of gas. Now, if in a mixture of gas, only particular quantity of gas exhibits the pressure, then we see it as what? Partial pressure of gases. Now, the expression for this Henry's law is mole fraction is direct proportional to P, partial pressure of gases. Here P indicates what? Partial pressure of gases. Now remove this proportionality constant, so the equation becomes P is equal to KH into mole fraction, where KH is said to be as what? Henry's constant, right? So partial pressure of gas is equal to Henry's constant into mole fraction of gas. So this is a graphical representation. So this is a partial pressure towards the y-axis, and towards the x-axis mole fraction. So we get, when we see a graphical representation with partial pressure of with mole fraction, we get a straight line, right? So that is the slope, and that is kh on Henry's constant we'll get here, right? So in the examination they may ask with respect to state Henry's law and give its mathematical expression. So Henry's law statement is at constant temperature, mole fraction of gas in liquid solution is directly proportional to partial pressure of gases. And the expression for that is what? Partial pressure of gas in liquid, that is P is equal to KH into mole fraction of gas in liquid solution. Now, sometimes they may ask, write the Henry's law equation and explain the terms. So Henry's law expression is what? P is equal to KH into mole fraction of gas in liquid solution. Now they may ask, explain the terms. P is said to be partial pressure of gas, KH is said to be mole fraction, Henry's constant, and chi is called as mole fraction of gas in liquid solution. Now you may ask, what is the application of this Henry's law? There are very important applications, right? There are three important applications. Please do remember this statement, because sometimes they may ask state Henry's law and give one application. So hence application is very important. As I had told, we'll study one first application. As I had told earlierly, solubility of gas in liquid, the best example is soda water. So here, soda water for soft drinks is prepared by passing CO2 gas in water, as I have told, at higher pressure, and CO2 gas usually dissolved. Now, I would like to give an example which you might have observed in your day-to-day life. Say, for example, I have got two soft drinks, Coca-Cola or Pepsi, anything, in which one of the soft drinks I place in a fridge or refrigerator, and I'll keep the other soft drinks outside. Now, which of the soft drinks is tastier, right? Now, you might observe this, that is, the soft drinks which is placed in the refrigerator is more tastier when compared to that of the soft drinks placed outside. Why? What is the reason? I think you might have known the reason for this. The reason is simple. Now, here, when I explain the pressure, I explain the application. here there is one statement that at higher pressure CO2 gets dissolved. Now when placed in a refrigerator, the gas has higher pressure. Since the higher pressure is present, this CO2 will get dissolved in the soft drinks liquid. So hence, then we'll get a taste. But the soft drinks which is placed outside, when you, there is no higher pressure outside, so hence when you open the lid of the soft drinks, the CO2 gas escapes. There is no proper mixing of the gas with the liquid, so hence the taste is not much good as that of the soft drinks placed in the refrigerator. So the first application of the Henry's law is, so soda water of for soft drinks is prepared by CO2 in water. At higher pressure, CO2 gets dissolved. Now, coming for the second application, that is at higher altitudes, atmospheric pressure in law as a result, solubility of oxygen in blood during respiration becomes small, which leads to disease called as anoxia. Right? So what is happening there is at a higher altitude, there is a high atmospheric pressure. What will happen if there is high atmospheric pressure? Oxygen gets more soluble in the blood, during which respiration becomes small, right? So that leads to a disease called as anoxia. What is anoxia? The incapability to think, right? So I think I'll explain this application easier. Say for example, if I go for Himalaya or higher altitude region, what will happen? The atmospheric pressure is greater. So if atmospheric pressure is greater, the oxygen which is present in us gets dissolved in the, or it is get more soluble in the blood. So if oxygen gets more soluble in the blood, it results into during which respiration becomes difficult, right? So due to which it results into a disease called as what? Anorexia. So what do you mean by anorexia? It is the incapability of to think, right? So I think you are clear with the second application. Then coming for the third application, at deep sea, pressure is high. Now see here, when you go for higher altitude, pressure is lower. I think pressure is low. It should be. It has become as law, right? So here at higher altitude, atmospheric pressure is low. Now, but at the deep sea, pressure is high. The nitrogen and oxygen gets dissolved more in the blood. When sea driver comes up there suddenly, the decrease in pressure, the pressure goes on decreasing. Now, when nitrogen and oxygen, what happens then? Nitrogen and oxygen tries to come out of the blood cells, causing a disease called as bend. I'll explain here the statement. What is the statement is telling here is, if a sea diver, right, if when he goes into deep sea, right, what will happen to the pressure? Pressure is higher. When pressure is higher, nitrogen and oxygen gets dissolved in our blood more. When the same sea diver comes above the surface of the sea, now at that time inside the sea pressure is higher, but when it comes outside the pressure is lesser. So hence pressure goes on decreasing suddenly. Now when pressure is higher, nitrogen and oxygen dissolves, but when it is lesser, so what will happen? So pressure, nitrogen and oxygen tries to come out of the blood cells. So that results into a disease called as what? A bend. Now, bend is a disease when the gaseous like nitrogen and oxygen, they try to come out of the blood cells. So that disease we got as bend. So please don't confuse with respect to anoxia and bend. So anoxia is occurring at higher altitude, whereas bend is occurring towards the lower pressure. Now, this bend can be prevented, right, by using mixture of helium and air. Now, you might have seen the sea divers, ಸಮುದ್ರದೊಳಗೆ ಯಾರು ಹೋಗ್ತಾರಲ್ಲ ಅವರು ಸಿಲಿಂಡರ್ ಒಂದು ಕ್ಯಾರಿ ಮಾಡ್ತಾರೆ, ರೈಟ್, ಆಕ್ಸಿಜನ್ ಸಿಲಿಂಡರ್. ಸೊ ಆ ಆಕ್ಸಿಜನ್ ಸಿಲಿಂಡರ್ ಒಳಗೆ ಬರೀ ಆಕ್ಸಿಜನ್ ಇರಂಗಿಲ್ಲ, ಅದ್ರೊಳಗೆ ಏನಿರ್ತದ, ಇಟ್ ಈಸ್ ಅಲಾಂಗ್ ವಿತ್ ದ ಹೀಲಿಯಂ ಇಟ್ ಈಸ್ ಪ್ರೆಸೆಂಟ್. ಸೊ ದಟ್ ಪ್ರಿವೆಂಟ್ಸ್ ಯುವರ್ ದ ಡಿಸೀಸ್ ಕಾಲ್ಡ್ as what? Bend. Now, Henry's law, statement, equation, the terms explanation and application is very important from your examination point of view. Now, apart from that, we'll study one more important thing with respect to Henry's law, right? So, the first thing you should remember here is, in case of Henry's law, greater the value of Henry's constant. So Kh is we call it as what? Henry's constant. Lower will be the solubility of gas at same partial pressure at same temperature or constant temperature. Now what do you mean by this? If the Henry's constant value is greater, the solubility of gas will be lower. That means it is said to be as Kh is inversely proportional to partial or solubility, right? So Henry's constant is inversely proportional to solubility, right? At same pressure and same temperature. Now, in one of the examination, they had given one problem, right? They will give you the two gaseous and they will give you their values. You have to identify which of these will be having lesser solubility, right? So greater the value, lesser will be the solubility. I think they were asked in the board examination many a times. That is nitrogen and helium are having the KH value so and so. Which of the following will be more soluble? So how to identify that one? That is by using here the concept as greater the Henry's constant value, lesser will be the solubility. That means lesser KH value will be more soluble. Now, the second important point you should remember here is the value of Henry constant increases with increasing temperature. This indicates that solubility of a gas, so it should be a gas, decreases with increasing temperature, right? So these are the two important points you should remember regarding the Henry's law. So we have discussed with respect to the solubility, saturated solution, unsaturated solution. We have started with the solubility of gas and liquid. Under that, we have seen the important statement given by the scientist called as Henry, that is said as Henry's law of gas solubility. We also have seen the expression for Henry's law. What is the expression? That is partial pressure P is of gas is equal to Kh into mole fraction of gas in liquid, where Kh is Henry's constant. Now we go for the next concept, that is called as a solution of or liquid in liquid, or I say it as a solubility of liquid in liquid. So earlier we have seen what solubility of gas in liquid, but here the solubility we are studying going to study here is what liquid in liquid. Now before I start for the solubility of liquid in liquid, that there is one term called as vapor pressure of liquid, right? So we need to understand the term called as what? Vapor pressure of liquid. Now, what do you mean by vapor pressure of liquid? It is the pressure of liquid in its vapor, right? Which is in equilibrium with its vapor pressure. The pressure of liquid, its vapor are in equilibrium what? With its vapor pressure. So I explain with respect to here one of the concept, that is here. You can see here. Now this is your pure water, say for example there is a above the surface, whatever is the pressure exhibited, that is said to be as what? Vapor pressure. I think you have understood here. So say for example this is a water, there is a surface of the water is here. Above the surface of water there is a pressure, right? So that pressure we say it as what? Vapor pressure, right? Above that, when it is in equilibrium with atmospheric pressure, then we say it as what? Vapor pressure. At constant temperature, the pressure exerted by the liquid on its surface when they are in equilibrium with atmospheric pressure is said to be as what? Vapor pressure. I think you understand the concept. Above the surface of this is atmospheric pressure. When this is in equilibrium with the pressure exerted by the liquid, then that we say it as what? Vapor pressure. Right? So vapor pressure of a liquid, I think you understood. So here now, based upon the solubility of liquid in liquid, we need to go for the concept called as Raoult's law. Now this is also very important law. In solubility of gas and liquid, we have seen Henry's law. Similarly, for solubility of liquid in liquid, we go for the statement by the scientist given by Raoult. We call it as Raoult's law. This is important statement. So we study first what is the statement of Raoult's law. So here, Raoult's law states that in a binary solution of two volatile liquids, In a binary solution, we know what do you mean by binary solution. Yesterday we have discussed of two volatile liquids. What do you mean by volatile? Which easily gets evaporated. Partial vapor pressure of each component is directly proportional to mole fraction of component in solution at constant temperature. Similar, I will explain the concept easily. Before that, I repeat once again the statement. The statement of Raoult's law is what? In a binary solution of two volatile liquids, partial pressure of each component is directly proportional to mole fraction of component in solution at constant temperature. Now, say for example, in one beaker I have got water, and they say for example that beaker I call it as A, beaker A. In one more beaker I have got one more liquid, say for example ethanol, right? That is, we say it as beaker B. Now, what is the statement? In beaker A I have got water, in beaker B I have got ethanol. Each of them exhibits their vapor pressure, right? Now, the statement is what? In a binary solution of two volatile liquids. Now, partial pressure of each component. Partial pressure of each component means what? The pressure exhibited by beaker A, pressure exhibited by beaker B is directly proportional to mole fraction of components in solution. That means when I am mixing A and B, whatever is the mole fraction of component, it is direct proportional to partial pressure of each component. That is component beaker A and component beaker B. So that is for binary solution. So say I said beaker A and B, so I take it as A plus B solution. PA. What is PA? Partial pressure exhibited by component A or beaker A is directly proportional to mole fraction of the component A. Now this is for binary solution A plus B. We can express this term, remove this proportional constant. We say it as partial pressure of component A is equal to K into mole fraction of A, where K is said to be the proportionality constant. Now, for pure components of A, mole fraction of A is equal to 1 and partial pressure of A is equal to P naught A. Here remember students, don't confuse with PA and P naught A. PA is partial pressure of component A, whereas P naught A is the partial pressure of pure component A, right? So therefore, if I substitute these values in the upper equation, PA is equal to K into mole fraction A, that is PA turns into P naught A, this should be P naught A, so PA is equal to K, so substitute value this, that is PA is equal to P naught into A into mole fraction A. So I think you understood here, I'll explain once again. For pure components of A, mole fraction is equal to 1, so here mole fraction will be equal to 1, K will be as usual, PA will be equal to P naught A equal PA is equal to P naught A. So substitute here P naught A is equal to K. So we know that substitute this value here. So when I substitute partial pressure, A is equal to P naught A into mole fraction A. Now this is the expression for your component A. Now when I go for partial pressure of component B, the same expression will be there. Instead of A, you have to go for component B. That is PB is equal to P naught B into mole fraction of B. Now we know that total pressure, I think in first year studied, right? Total pressure is equal to partial pressure of components, right? So Avogadro's law of partial pressure we have studied, right? So formula is what? Total pressure is equal to partial pressure of each components. So which is the partial pressure here? Partial pressure of A and partial pressure of B. So that is equal to what? PA plus PB. Now we also know that mole fraction, I have when I discussing, I told mole fraction of A and B is equal to 1. So mole fraction of A will be equal to what? 1 minus mole fraction B. Now substitute these values here. So you can see here earlier term I have taken here, partial pressure is equal to P naught A into mole fraction of A plus P naught B into mole fraction of B. Now substitute value, what is the value of mole fraction of A? That is 1 minus mole fraction of B. Now what will be the final expression? P naught A, multiply here everything, P naught A is plus P naught B minus P naught A is into mole fraction of B. The above equation is similar to that of y is equal to, so P, I forward right here P, so y is equal to mx plus c, so the same equation, this is a mx plus c. So hence we get a straight line when we plot a graph of vapor pressure versus mole fraction, right? So in Raoult's law, it is very important to remember, students, the statement. If you're unclear with the any part, right, that is regarding it, may be with respect to the expression part. Now remember, I had told earlier, I have taken beaker A. I will write it as the pressure exerted by the beaker A is said to be as PA. I have taken B beaker. The pressure exerted by beaker B is PB. Now when I am calculating the partial pressure of each beaker, so we can write the expression as what? PA is equal to P naught A into mole fraction of A, where PA is partial pressure of component A, P naught A is partial pressure of pure component A into mole fraction of A. This is for beaker A. Similarly for B or beaker B, the partial pressure is equal to P naught B into mole fraction of B. These are the two expressions for your Raoult's law. So if in the examination they ask state Raoult's law and write the expression or mathematical equation. So statement is clear. It is in a binary solution of two volatile liquids. Partial pressure of each component is directly proportional to mole fraction of component in solution at constant temperature. At constant temperature. Now the expression for Raoult's law is PA is equal to P naught A into mole fraction of A and PB is equal to P naught B into mole fraction of B. Now remember to write both the expression. Don't write only any one of the expression. You write both the expression. Now this is all with respect to the solubility of liquid in liquid. So key points to remember: for solubility of gas and liquid, we have the statement given by the Henry and its application and expression. For solubility of liquid in liquid, the statement given by Raoult's law is statement and its expression. Now, before we go for the next concept, what is the next concept we are going to study is uh, we are going to classify the binary solution. That is classification of binary solution. Now, binary solution, we know there is presence of a solute and solvent together forms a binary solution. Binary solution can be classified into two main classes called as ideal solutions and non-ideal solution. This is very important concept, dear students. Most of the time it is asked in the examination, right? So ideal binary solutions are mainly classified into two main classes called as ideal solution and non-ideal solution. I am going to tell first concept called as ideal solution. Don't, dear students, don't confuse with the ideal gas with ideal solution, which you are studying in first year. Ideal gas equation E is equal to nRT. That is will change with respect to that of your ideal solution, the concepts, right? So some of the times it is observed that if you define ideal solution, you write ideal gas equation, right? So ideal solutions is the concept related to that of solutions, right? So here, how to define or what do you mean by ideal solution? Ideal solution is defined as a solution which obeys Raoult's law at all concentration and temperature. Is called as what? Ideal solution. So the definition is very easier one, right? So how to define an ideal solution? It is a solution which obeys the Raoult's law. We have studied about Raoult's law. That is in a binary solution of two liquids, volatile liquids. Partial pressure of each component is directly proportional to its mole fraction of components in solution. So if it obeys the Raoult's law at all concentration and temperature, then that solution is said as what? Ideal solution. Now, dear students, it is being observed many times that when they ask the definition of ideal solution, most of the students write the definition as it obeys Raoult's law, or a solution which obeys Raoult's law is called as ideal solution. Now, it is better to write the definition completely. Now, what is the definition? As I told, it is a solution which obeys Raoult's law at all concentration and temperature. That solution we say it as what? Ideal solution. Now, what are the characteristics of ideal solution, or what are the things you should remember regarding the ideal solution, that we will see in the next class. Now, before I wind up this, please see the video again and again, understand the concept, since we can't teach in the classroom now at present due to COVID-19. So please see the videos and understand the concepts. So if you have any doubts, right? So please do reply or ask the doubts properly. So I, I I hope that you all see this video and understand the concept, right? So we will see the next concepts in the next class, right? So wish you all the best. Thank you.